Hey everybody, we're going to go ahead and get started. My name is Sean Meyer. I'm here with Mark Nuppnau. The motivation for this talk actually came from a previous Midas talk that Dr. Mike Schoding had presented on some of the work that he had done around LLM analysis or LLM research for one of his projects. And I connected with Mark, and we started discussing around actually showing people how what a good starting point for that was. So the premise is we have access to a lot of these resources at University of Michigan, one of them being UMGPT, which is from a technical standpoint a virtual private cloud of OpenAI's ChatGPT endpoint. So I know that was part of the presentation previously, but we also wanted to show how we might be able to do this specifically for research projects here at University of Michigan, utilizing the resources, the computational power and the storage that we have using the high-performance computing cluster here at U of M. So a little bit about the agenda. We'll go through how to, so the framework that we're using is actually called llama.ccp, or CPP, excuse me, because it's using C++. That framework can actually be used to launch a plethora of different open source models that you can actually download from the web and actually run locally on these machines. I'll talk a little bit about advanced research computing, which is the group that manages these resources here on campus. I'll talk a little bit about the generative AI policy for Michigan medicine, because that's going to come into play not only for how we use UMGPT, but also how we use the ARMIS resources as well, what you can use PHI on, what you can't use PHI on, that type of thing. We'll go in a little bit about the usage of Llama. So there's a couple different ways that you can use it. You can use it via command line. If you're familiar with Shell, you can also use Python to invoke the LLM and generate inferences. And then I'd like to talk a little bit about use cases and maybe open it up to other people to tell me what they're thinking around use cases, because I'll get into it a little bit different, a little bit later around like business operations. But I work on the machine learning operations team at Michigan Medicine, and we're really interested to see what people are generating as far as ideas on how to use these and these research projects in operations, both business and clinical operations. So without further ado, I'll go ahead and, well, I'll talk a little bit about the prerequisites first. So like I said, you'll need access to ARMIS2, which is the PHI HIPAA compliant computing cluster here at University of Michigan. You can gain access to that through the U of M research computing package if you are if you do a faculty member doing research. If you are a staff member, you can also utilize that as part of a lab. So you would connect with your faculty and gain access to those resources. Another option is, again, if you're faculty, you can use the Precision Health membership. Precision Health has their own cores and GPUs that you can generate inferences on. I put a couple links in the slides, which hopefully we can just share a link out for people that want to follow that. If you already have access to that stuff, I think you're pretty much set to go. And we'll of course answer any questions around technical difficulties specific to this example that you may encounter. Maybe we can walk through them if we have time at the end. And then, of course, you depending on which way you want to use it, you'll have to have some sort of experience with Python and Shell. We'll give you everything you need to know as far as what to use. But if you have any troubleshooting, if you want to do any more advanced analysis on that, you may run into some issues. But there's a plethora of information online around, and UMGPT, of course, to figure out what your problem is and to get to the answer quickly. So I think I already kind of touched on this, but the objectives of this lecture is to show you kind of an overview of how to prepare the environment for building out the Llama framework, which supports these LLMs, interact with the LLM via command line interface or shell, and then I'll even show you how to start an API server, very similar to how we use UMGPT. So the advantage of that is if you're already using the UMGPT toolkit, this will be a very smooth transition from that framework over to using something like this. And I'll go into a couple details about what the features might be for that. And then Mark is going to show us how to use LangChain to chain together multiple conversations, either with the same LLM or different requests using the different LLMs, right? So basically, the premise to that is building out agents that can actually automate a lot of the process around using LLM inferences in multiple different steps that you might otherwise have to do manually. Down at the bottom is a link to the notebook that we will be walking through that should have all the code that you need to be able to get started and do what we're going to be showing everybody. It should be in the chat, and it'll also show you kind of what the output that you should expect from something like this. A little bit more about advanced research computing. Again, ARMIS is the high-performance computing cluster that is HIPAA compliant. There's the Turbo Research Storage, which is part of that U of M research computing package, and can be used with sensitive data when you set it up. Basically, when you go through the process of requesting provisions for those resources, you basically identify either whether you want sensitive data approval or not, and then how much of your total allocation you want. DataDen is basically considered like cold storage, so you like back up all your projects on there. It's not as it doesn't have as high throughput as Turbo, but it's really used as kind of an archival area. It's best practice to move old projects off of Turbo onto DataDen just to free up those resources for everybody else. And then the last piece, which we'll go through, is Open on Demand. So Open on Demand is basically using Jupyter Lab, Jupyter Notebook, Visual Studio Code, as well as other applications in a web-based interface. So you don't need to install any software on your computer. You really just use the web browser to interact with these via either shell or via Python. Going to go really quickly through the guidelines. So if you have questions about what you can and can't do, this is likely where you will find the answer. So there are two different policies. One is the appropriate clinical use of generative AI intelligence tools, which is more of a clinical policy, so how we would use these in clinical practice. There's a little bit of overlap between these, just basically kind of giving information about what does non-deterministic mean. It basically means if you provide an LLM with the same question, you might get different responses. You might even get different responses between the same LLM or different LLMs, just to make you aware of that. There's hallucinations, which are really just kind of errors of commission of the output that comes back might be wrong. So it's important to have a human in the loop on all of these tools or use cases that you develop. There can be biased outputs depending on how the model was trained, where the model is coming from, and then any guardrails that were built into the model itself. And then, of course, I already kind of touched on this, but automation risk. So making sure that someone is reviewing this before it's used in any research or clinical workflow capacity. The other piece to this is more of a technical overview, which I think is probably going to be more interesting or at least relevant to the discussions that we're going to have today, talking about what a web-based generative AI tool is. So basically something that is internet accessing, right? So if you go on perplexity.ai and you use the search engine, if you use Google and you see results that come from I think a Gemini is the Google model. Basically anything that isn't kind of predefined for the use of sensitive data that is web-based, that could possibly either be used to retrain the model or be used as part of the output in future models. So you just have to be careful of that. Right now, there's no enterprise tools at Michigan Medicine that can be used with sensitive data. with the exception of what I'm about to show you with ARMIS. I'll put a little asterisk because I will talk a little bit about UMGPT and how you can use that for limited uses for PHI, but I'll get into that a little bit later. But what I will be showing you is how to use local generative AI tools. So this is the Llama framework. This is downloading the actual model, which they can get pretty big, gigabytes, terabytes of model objects that you can then use to run inferences using GPUs or even CPUs in some cases. So if you have any questions about this, feel free to consult these. The links are in these slides, but that's kind of where that information comes from. So we'll go really quickly through. Are you going to do this part? Okay, so we'll show you how to kind of set up the environment. There is a little bit of pre-work that you have to do to kind of get the LLM downloaded and get the framework set up, so then you can do all these other cool things that we're about to show you.
Thanks, Sean. Yes, we're going to go quickly through an environment setup pretty early in the presentation because one of the steps in the setup takes roughly 10 minutes or a little longer to run. And so for anyone who's following along and running code, we would like to have you on the same page as we go through the demos. So the first thing we're going to do is go to, as Sean had mentioned earlier, the Open On Demand web-based interface for Jupyter notebooks. And you could either select an interactive app for Jupyter Lab or a Jupyter Notebook. In this case, we have a Jupyter Notebook running. And the fields that we want to fill out here, we have a Python distribution. We're currently using Mamba, Python 3.10. You could also select Anaconda. I don't believe that would be any issue using that as well. And so we also need to select a Slurm account, and I have access to Precision Health Owned 1, but you might have an owner or username-based account here that you would be selecting. And the partition we select is Precision Health, and that allows us access to the Precision Health GPUs. And again, if you don't have access to Precision Health, you would want to select a GPU partition, like so. And number of hours is just the number of hours you want your session to run for. For these demonstration purposes, maybe 2-3 hours should be plenty of time to walk through the demonstrations. Number of cores, this will also depend on the partition that you have. If you're selecting Precision Health, as it says below, Precision Health or GPU as your partition, you could select up to 40 cores. And one reason we select a higher number of cores for this initial session is because we're going to be building llama.cpp, the repository, and you can run jobs in parallel, and you would want those number of jobs to be equal to the number of cores you select. And so this will help speed up that process. And memory, we just select 40 gigabytes for no particular reason. I'm sure even 10 gigabytes would be plenty for what we're doing. Number of GPUs, we're only requesting 1 GPU so that others following the demonstrations can also potentially have access to GPU. And the last step that's important is loading these modules so that the building of llama.cpp can run properly. And so you want to load GCC, CUDA, and CUDA-NN, and then click launch. And that's going to launch your session. So as you can see, we currently have a session running. And you would want to either start a new notebook, or if you had downloaded the notebook from the GitHub repo, you would want to utilize that. So this is our notebook, and we're starting with just looking at where we are, our current working directory. And as you can see, I'm on my home directory within a projects folder. But for future reference, when you're working with larger models, you may want to use the Scratch directory as opposed to the home directory, as you'll likely run out of storage space when you're working with larger models. And so the first step you'll want to do is install Llama CPP Python, and this will require GPU access. Otherwise, the install will fail. And LangChain, which we'll get to later, will be utilizing this package. And then we'll want to install the other packages, OpenAI, LangChain Community, Pandas, and PyArrow. And so we'll give it a few seconds here. If anyone is actually running this, it shouldn't take too long. Okay. And now we're going to get to actually cloning and building llama.cpp. So there's a question. Okay. So we have a question. What is llama.cpp? Llama.cpp was originally a framework built to efficiently interact with Llama models. And it was built using C++ to make that as efficient as possible. Is there another?
Yeah, if there's a question online, go ahead and unmute yourself or put the question in the chat.
Should be able to put it in the Q&A section.
Yeah, it's a webinar, so they can't.
Oh, in the Q&A, please. Thank you.
Okay. So the first thing you'll want to do is clone llama.cpp, and that'll be a pretty quick process. And you would want to move into that directory.
The GitHub link might have an issue.
They have to log into their U of M account. Okay. Otherwise, you can't have it.
Right.
You can access it through the U of M account.
Yeah, that's correct. If you're trying to access the GitHub link that we provided, you need to log into your U of M account. Oh. Okay, so there's another question. What if we use precompiled binaries for llama.cpp? Yeah, that should be fine as well. I haven't personally done that, but I don't see any issues with using precompiled binaries.
It may also depend on the model because they constantly update that platform. So as new models come out, they continuously update that Llama CCP. So I would give it a try, but if it doesn't work, you may have to update the repo.
Yeah, I would imagine the precompiled binaries aren't updated as frequently as the repository, right? And so after you clone the repository, you want to move into that repository directory. And then we want to build llama.cpp. And so the first piece of code here is a configuration phase, which generates the build system. So that's going to create all the make files that the build is going to utilize. And that's a pretty quick process. The longer process here is the actual build phase, which compiles the source code using that generated build system. And as you can see here, we set the number of jobs to run parallel equal to the number of CPU cores we have, which is 40. And this, with 40 jobs in parallel, will take roughly 10 minutes. And if you have less number of CPU cores, it'll likely take a little longer. And so while that is building up, I'm going to pass it back to Sean to discuss a couple different topics here. Yeah, so if anyone's having issues still accessing the GitHub repo, I can make that public. Should I just do that? Yeah. Okay, so this repository should be public now. There shouldn't be any issues accessing it. If you do have any issues still, please let us know.
Okay, thank you. So we already covered kind of the difference between the local and the web-based. What we'll be showing you today is, again, we're going to download the model, and we're actually going to show you how to run inferences on the local model. To answer the question, so I think we just opened up the repo to be public. If you try refresh the page, or refresh the link, or click it from the chat again. If you continue to have problems, let us know, and we'll see if we can work that out. So just wanted to talk really quickly about some of the use cases. I'm also interested to hear from the attendees about maybe what ideas you have around use cases for this. Some of the things that we found in both the research and the operational in the research area as well as in operations is de-identification of data sets. Using or generating synthetic data. We've actually tested generating synthetic data from the LLM as well, and that works pretty well. Note summarization is a big one that there's a lot of interest from the clinical workflow side for utilizing EHR data, pulling data in from all over a patient's medical record and then summarizing it and providing sources for where that data exists. Programming and coding, if you're familiar with like GitHub Copilot, a lot of these models have specialties. So like GitHub Copilot is specifically better used for programming, but I've also tested it with, like, for example, the Llama model that we're about to show you, and it actually does a pretty good job of at least giving you like pseudocode, and then you can kind of go in and build from there. Converting unstructured data to structured data. This is also a really big interest in the operational clinical operations. And I think we'll be showing you a little bit of a snippet of kind of how we plan to do that. One of the advantages of using the OpenAI framework, whether it be UMGPT or the one that we're going to show you, is actually you can have structured data returned to you. So you can actually ask it for a JSON object, you can convert that JSON object to a data frame, and then you can export that data frame as a CSV or whatever other structured job you have. There's also helper chatbots. So similar to like Maisie, using retrieval augmented generation, where you have a knowledge base that you build on top of the LLM. You provide it context for based on the type of data that you want it to respond to people, and you can use something similar to like Maisie to build these helper chatbots. I think we've already touched on a lot of this, but I did want to reiterate that the Llama CPP framework, like Mark said, it was originally used to make using LLMs more efficient. There have since been a lot of support for a bunch of different LLMs. I think if you go to the GitHub repo, it has a big long list of the ones that it supports. And like I mentioned earlier, they're updating it all the time with the new LLMs that are coming out. Quantization. One of the concepts of quantization is actually reducing the size and increasing the efficiency of LLMs. Now, you do lose some power in terms of inference, and I think Mark's going to touch a little bit on the size of the models, and what if you see like something that says 3B, 7B, 70B, what that actually means, and kind of how to use that in the context of what you plan to do. Obviously, larger models are going to have most likely more useful inferences depending on what you're trying to do. And then that kind of ties in with the next point, the parameters. So looking at something with more parameters is going to be larger, but it's also going to require more computing power in order to generate inferences. I already touched on RAG, so I'll go ahead and skip that. But that's essentially, like I said, Maisie. You can basically build a knowledge base that you can then use the LLM to generate inferences on. I just popped a couple other ones that we've kind of explored. Qwen Coder 32B, that's obviously like something that can help you with coding. DeepSeek R1 is actually a new one that just came out, and it's the benchmarks so far actually show that it rivals like GPT-01, and hopefully we'll see even more improvement from that. There's a link in there if you want to check it out. They also have some distilled versions of other open source models using that DeepSeek model to kind of make them more efficient, make them use fewer resources. A little bit of the flow or the process by which I think a lot of our projects go, or could go. So for example, you could start with UMGBT because the barrier is pretty low. You essentially just need a short code to get up and running. The AI group over at ITS will actually provide you with starter code similar to what we're about to show you for the OpenAI framework, but it's very good for like exploratory research. There is a limit on how much PHI you can use, and it requires an exception exception to policy specifically for the project that you're using. And I think I think it's around 5,000 records is typically the requirement. But I think it's a good jumping off point. So if you're looking at just kind of getting started and seeing what you could use it for, an LLM, what you can use an LLM for, to seeing if it's even worth your effort, that's a good use case for that. And then, so again, ARMIS2 and Turbo, what we're about to show you, if you're really looking to scale up your research, or you want to try a bunch of different models other than what OpenAI or UMGPT offers, you can do it that way. It also is approved with PHI, and again, when you set up your turbo volume, you do have to indicate that you want to use it for sensitive data, and it basically just has different security requirements around it. And then, so a future state that we can kind of see, and this is why I'm interested to see what people want to do with this, is that there could be on the operational side, once we look to translate that research into operational practice, clinical practice, we'll be looking at using secure cloud providers to be able to do something like that. So that's in a future state. We don't currently have that available, but hopefully soon it will be. Okay, so I'll turn it back over to Mark. He's going to show you how to download the model, and we'll go through a few different steps and show you how that's done.
Thanks, Sean. Yeah, so hopefully your llama.cpp repository is close to finished building. And okay, so there was a question earlier, what are the tasks being built? So we're assuming you're referring to building llama.cpp. So there are various objects being built here that we're not going to utilize, but here are some of the objects that are being built. Okay, and so hopefully that's close to finishing for everyone. And so now we're going to move into the models directory of llama.cpp. And we're going to download the model here. And so this is going to take roughly a minute or so to download roughly 3 gigabyte model. And so this model, Llama 3.2, has 3 billion parameters. And the GPU VRAM that's going to be required to run typically any of these models is roughly the number of parameters multiplied by 0.8. So for example, this model has 3 billion parameters. And if we multiply that by 0.8, we get 2.4 gigabytes of required VRAM. So that's a rough estimation of what you can likely see in the future. And Sean touched on this in a prior slide. So the number of digits stored for each model weight would determine the file size of the model. And if we look below, we can see different variations of Llama 3.2 and different file sizes. So for example, the top model here, Q8, so that's referring to these model weights being stored in 8 bits. And that produces extremely high quality output. And so you can see as we reduce the number of digits stored for each model weight, you lose some quality of the output. So there's a trade-off there. And so for example, this Q5KM, so the file size is reduced to 2.32 gigabytes, and you're still getting high quality output. But when you move down to 3 or 4 bits for each of those model weights, you're starting to lose quality, even though you're reducing the amount of storage space and VRAM required. There's a question about the RAM required to run these models. For the most part, with the demonstrations we're going to show, all of the processes are going to be ran on the GPU, so the RAM requirements are very low. I believe I mentioned earlier we had selected 40 gigabytes for this session, but I believe 10 would be plenty for this demonstration. And so going back to the notebook, the model should be downloaded now, and we're just going to rename it here and move back to the llama.cpp file path. And so we're actually going to go ahead and run this now that we already had this repository built, and we're going to test this llama CLI and we're going to feed it a prompt to create a 3-paragraph synthetic clinical note for a patient who presents with sepsis. And we're going to offload all of this work onto the GPU.
Yeah, and I just want to add, up until now, what Marcus showed you, anything that has like an exclamation point or a percentage sign in front of it, this is all via shell. So we're using the Python notebook to run via shell just for convenience, but you could essentially do a lot of this directly in the shell. So with Jupyter Lab, you can actually open up a terminal and type it in command line. We're doing the exact same thing here, but we're just doing it block by block just so we can show you what's the progress over time. What I will show you in a few minutes is then how do you use it with Python, which is just a different way to use it.
Yeah, that's a great point, Sean. And I tried to capture that in our GitHub repository here to provide two different methods for each of these commands. So there's a shell method, which Sean touched on, where you're not going to need these additional symbols to run these commands.
Yeah, and if you use that nproc variable, that really just pulls from the shell how many processors you are. So instead of like in the example that we're using 40, you could actually just use that line and it'll use however many CPUs you've got.
That's right.
There's a question about, can you monitor the GPU process while it's running? So what I found, I guess the answer is kind of. So if you open up a terminal and while you're on ARMIS and you type in top, you can actually see all of the different processes that are running on that cluster at the time.
And you could also, if you wanted to see if there's anything currently running, you could use NVIDIA SMI, and that will give you, it'll list any processes that are running. And right now, we currently don't have any because it completed. But as you'll see later, we'll have a Llama server process running that would show up.
Yeah, and you can also see here what the memory usage is, and more specifically what I'm interested in is the amount of RAM that's on the GPU. So you can see that there's 11 gigs of RAM on the GPU. I know the difference between the Precision Health ones and the regular clusters might be a little bit different. So you may also have to factor that into the amount of RAM that you need to run the model, because you typically want a little bit of overhead beyond how big the model is just to generate inferences.
Yeah, exactly. So for example, like I had mentioned, you would want roughly 2.4 gigabytes of VRAM for this one model. You would want to make sure that's for loading the model. You want to make sure that you have additional few gigabytes for the inference process. And so I'll pass this back to Sean for his demonstration. And you could probably go through that process too. If you don't have to run it, but just.
Okay, so in this example, we're actually just pulling up a synthetic data set that is available if you just use this to download the CSV file. This is actually what we're going to be using. You can of course use your own files as well, but this is the one that we'll be doing in the example. So in the OpenAI demo, this is kind of where we change over from, remember, command line, which all of these are shell-based commands. We're going to be moving over into more of the Python space, which is more appropriate for Jupyter Lab. I've also done this in Visual Studio Code, so this does work for Visual Studio Code on the cluster if you're interested in using that as well. So we'll be loading some packages here. This, if you are familiar with the toolkit, this is very similar to the code that ITS provides you. We're essentially setting up in the code. Did I miss a step? I think we need to start the server, right?
How about just going to Jupyter Lab?
Oh, here we go. Okay, so if you see, is this on the notebook as well?
No.
Okay, I'm going to go ahead and copy. I don't know if it's on the notebook in GitHub, but we will go ahead and get it there. But I'll go ahead and paste it into the chat. So the assumption here is that you're in the llama.ccp folder, and you're going to do this either, if you're doing this in Jupyter Lab, then you'll be putting an exclamation point in front of it, right, to get it to run. But since I have a terminal open, I'm going to go ahead and do that. It's going to open up a bunch of stuff. Hopefully, it basically, it shows you that it's running on the local host, and that all slots are idle. So now, back to the notebook. When we go through and test this, so what we're doing is we're setting up the client. We're telling it that we're going to be running it on, this cluster. I think you need to have this defined, but it doesn't matter what the API key is. There's no API key for this. Normally for OpenAI, you would use an API key in order to access it. And that's, of course, tied to billing. So if we run this, we're going to be loading in our synthetic data. And then so we're going to define the system prompt here. We're basically just telling the AI what we want it to do. So your task is creating structured data elements from unstructured clinical notes. I want you to return a JSON object with the following keys. This is something that's, I think you can play around with depending on how complex the data that you're using is. But this is essentially like you're giving it instructions with every single user prompt or every single note. So this is what you're going to be repeating to it every time you ask it for an inference. So we'll go ahead and set that. This is more just more setup, basically defining a function that makes that call to the endpoint. We're telling it that we want a JSON object in response. You can give it a temperature. More towards 0 is going to be more deterministic, meaning the response you get will be more repeatable, whereas more towards 1 will give it more kind of that creative response, but may introduce more additional hallucinations or errors. So depending on the data that you're working with, again, or what you're actually doing with it, summarization versus generation, you may want to play with that to see how it behaves. And then so this block of code right here, we're just creating a new data frame. Creating a new data frame. We're running through a loop and basically asking it, asking that function that was above what, along with the note, we want to return a JSON object. We're also asking, and this also works with the UMGPT, you can actually get the tokens back. So you can, if you wanted to do calculation on how many tokens there are or what it would cost for like UMGPT, you can make that comparison. We're appending that to our results data frame. We've got some error handling right here. And then we're just basically just calculating how long all of that took. So it's currently running through, I think we did 10 rows out of that 15,000 row, 158,000 row CSV. Looks like it completed in about a minute, which is great. We are, okay. Yeah, so running this basically just collapses it down into a data frame, and then we're saving it as a Parquet file, which if you're familiar with, gives you the structure and the compression to be able to save those files. It's a little bit more efficient than CSV. It takes less space, and then it also preserves what those data types are. So you can see from the output, I saved what the prompt was, what the original note was, and then I really asked for what the age of that patient was, what the diagnosis was, and then I gave it a summary. I know it's kind of cut off, but that's essentially, I think I asked for like a short summary of what is in the note, and then you can see like what the tokens are, what was in the prompt, what was in the completion, and what the tokens. Yeah, is there a question?
There is.
Yeah. Yeah.
So in the diagnosis output, it's the fact that like in row 1, not 0, row 1.
Oh, yes.
Does that mean that the model basically didn't quite get the JSON structure right in its output?
That's a good point. Yeah. So the question is in this row that I have highlighted, what's the deal with the brackets and all that? So it looks like what it actually tried to do is return a list. You will have differing results depending on what model you use and what you use in the prompt. So I tried to be as simplistic as possible in the prompt just for demonstration purposes. But you can add more context. You can say, give me the chief complaint, chief diagnosis, something like that, perhaps. Or you can just use this and parse this out if you wanted to.
So what you're saying that this seems like the model is trying to list
I would imagine that might be due to the smaller size of this model, whereas a larger model, such as a 70 billion parameter model, wouldn't have issues similar to this.
Okay, so good timing for my cough. I'm going to turn it over to Mark to demonstrate the lang chain.
Sure. Thanks, Sean. And so, as I showed earlier, we could see our GPU processes with NVIDIA SMI. And we can see that the Llama server process is still running, so we're going to need to stop that.
So it shows you how much memory it's using too.
Right, and it does show you the amount of memory being used. And when we started that process in the terminal, if you're wondering how we got to that, you just click the Jupyter Lab button here, and that opens up a Jupyter Lab window. And you can select running terminals and kernels to start a terminal process. And we're actually going to go ahead and stop. We're going to shut down this terminal process so that I can utilize that same GPU now. Yep, and so we're going to rerun that and see that there is no running processes found anymore. So now we can move on to the LangChain demo. Just a quick overview. The usage for LangChain, it allows for simplified interactions with LLMs, and it chains together various elements of an application, whether that is different LLMs or just a single LLM. And so there's various types of chains as well, and the one that we'll utilize is called an LLM chain. And this is where user input is passed into a prompt template, and it transforms that input to a prompt that the model understands. And then the prompt is passed into an LLM to generate the output. And an option that isn't required is that you can pass that output into an output parser to format the results. For example, if you wanted to output a JSON format. And also another chain is sequential chain that just combines individual chains so that you have a continuous sequence of chains. So we're going to go ahead and import the packages we need. And we're going to set up callback manager, which is optional. This allows you to see the output of the LLM as it's running. Okay, and here we're going to set up the Llama model with these parameters. We're going to set the GPU layers to -1, which means all of the work is going to be offloaded to the GPU, assuming you have enough resources for all layers. And if not, it will offload as many as possible. And we have nbatch, which is the how many tokens can be processed in parallel, and the context window size, and the maximum tokens, which I just set to 100 since we're not asking it to do a lot. And so we have two LLMs here. You can see we're using the same model for both LLMs, but one of the benefits of LangChain is that you could utilize different models. And so this is for simplicity, but this could easily be two different models that interact with one another. So we're going to go ahead and run that. And so this loaded the models for us. And now we're going to create that prompt template for our input. And so we're going to have 3 templates. Our first template here, we're telling the LLM that it's a medical expert, and we're providing it a clinical note, and we want it to provide the most likely primary diagnosis given that note. And then the second template is going to be utilized by the second LLM, and we're going to tell it that it's a medical consultant and to review the clinical note and the primary diagnosis from the original LLM and state whether they agree with that diagnosis. And then the third template, we're going to utilize the first LLM again and provide it with the original note, the primary diagnosis, and the response from the consultant, and see if it wants to revise its original diagnosis. Oops. So okay, that ran. And now what we want to do is chain together each of those prompt templates with each model. So you can see here we're chaining together prompt 1 with LLM1, prompt 2 with LLM2, and then prompt 3 back with LLM1. And then you want to create a final chain that's an overall chain of those individual chains that we created. And in here, we're going to create that list of synthetic notes, similar to the notes that Sean utilized. Here's an example of the first note in that list. And we're going to invoke that overall chain to run for each note. And we can see here, for the first note, the first primary diagnosis is ARDS. And the second LLM seems to largely agree. And the first LLM does not want to revise its original decision. And so it's going to run through 20 separate notes and append it to a list of responses. So that finished running, and we could take a look at the responses here as an example. Yes, so we can see here it's possible that the first LLM will revise its decision, even though it was the same model that was being used. But so for example, something more interesting than this might be is if you have a larger parameter model that's used for more general work such as text summarization, and then you have a fine-tuned model that does more specific work, and you have those LLMs interact with one another. And that is the end of the link chain example I have.
Yeah, so thank you. So I provided a few, just a few links. First one is just some of the commands that we used are actually from the llama.cpp GitHub repo. So if you wanted to see more stuff that you could do with it or more complex stuff, you can look at that. Next is how to set up your environment in Visual Studio Code. It's a little bit more complex than what we showed you here. So didn't want to totally go through that just because it might take a little bit longer. Third is a little bit more information around ARMIS2 and an access guide for researchers. Another document below that is building effective agents. So this kind of touches on like what are good use cases for using LangChain, basically using different, basically chaining different either LLMs or different tasks together. Why would you do that? And you know, how could you use kind of the agent framework to do something like that? Of course, couldn't speak without the University of Michigan Sensitive Data Guide. If you have questions about whether you can put data into some sort of data source or data storage, definitely consult that. Again, in this demo, we used ARMIS2, which is the computing cluster that is HIPAA aligned, and we also use the turbo drive. And this is maintained by Advanced Research Computing. A little bit more documentation on that Llama CPP Python package if you want to know more about that. And then lastly, a little bit of information about that DeepSeek R1 model that I had talked about. We didn't do a demo for that in this demo, but it does work with Llama CPP if you're interested. It's one of the newer ones that just came out this week. That is all we have. We thank you for your time, and we thank Midas for providing resources for us in this lovely venue. If there are any questions, we'll stick around for a couple minutes, but otherwise, please utilize either the QR code or click on the link or I guess use the QR code or the link above to go to the feedback, the feedback survey, and then the bottom link is for, I think there's one more tutorial series, right? One more? One or two, okay. But if you want more information about the future tutorials, please use that link. Please use the feedback form to tell us whether this was useful or not. I know in this particular session, we did a little bit more of the applied analysis for some of this stuff. I know in past sessions, it's been a little bit more theoretical, just really interested to see what you think about whether this is useful or whether you're looking for something entirely different around AI and how it can be used. Thank you. Oh, we got a question? Okay. The OpenAI model demonstrated is free. So, so just in the way that there's the Llama CPP framework and an actual Llama model, there is an OpenAI framework and an OpenAI model. But in the demonstration that I gave you, what you are actually doing is running the Llama model, but you're using the OpenAI framework in order to connect to it, if that makes sense. So you're using, basically you can use the same code that you use for, or similar code, I should say, that you use for like using the UMGPT toolkit, but instead of connecting to UMGPT, you are actually just connecting to your local instance of the model on ARMIS. Hopefully that answers your question. Another question?
That you put not definition of text in the problem. How important is that? I mean, for the prompt engineering on this part?
Yeah, I could speak to that.
Repeat the question.
Okay, so the question was, we included a text in a string of text in the prompt to the LLM to not include additional text. And the question is, how important is that? For these smaller models and for some of the older models, such as Llama 3.1 or previous versions, it seems pretty important to include such a string of text. For newer models, though, and especially the larger ones, such as 70 billion model parameters, it doesn't seem to be as needed as those smaller ones.
Yeah, and also add an example. So one of the projects that we are currently working on is converting Oracle SQL over to Microsoft SQL code. And in using the toolkit specifically, what we had to do is actually tell it not to return any additional text other than the converted file. So like if you go on UMGPT and you say, I want you to revise my Python script, right? It gives you a bunch of extra context before and after about what it's doing and why it's doing it. But I know with UMGPT and probably with other models, which Mark kind of touched on, is you can actually be explicit about exactly what you want it to return. And sometimes that's just the response and not additional context that is included in that. Is that helpful? Okay, thank you. Llama 3.2.
That's correct. So the model that we utilize is Llama 3.2. It's the 3 billion parameter version of that model.
Yeah, and I think so. You know, in exploring this, you need to find the sweet spot between the prompt that you're giving the model, the information that you want back, and then the amount of resources you have. So in this demonstration, we only used one GPU. And so we're using a pretty small model. I think the 8 billion parameter model, but it goes up to 400. Okay, yeah. It goes up to much more than that. So it's really about starting small and then kind of building up. If you're unhappy with the results, you know, going up to a different, you know, the next step up, and then boosting your VRAM for your GPU or more GPUs if you need those, to be able to find what the sweet spot is between the amount of resources that you have and the information that you're trying to get back from the LLM. Okay, the question, going back to an earlier question, what is the advantage of using Llama CPP versus simply using the Hugging Face libraries? Are there any plans to support OLLAMA on the clusters? So to the second question, the clusters are maintained by ARC. So unfortunately, I can't answer that question, but that might be a good question for them. If you want to reach out to them on their website. I don't know that they plan to support any of that, but it's certainly worth asking if you're interested. Or Docker support. Yeah, I'm not aware of any interest in supporting, at least from an advanced research computing perspective on the clusters. It's really just providing compute and storage, and I think pretty much the rest is up to you. They do have modules on there, so that might be a good way to frame the question is, you know, do you plan to add a module for OLLAMA or Docker, something like that? I think one of the limitations that you'll find with ARMIS is that because of the sensitivity of the data, is it's pretty well firewalled off, so you can't really get data in and out from like an API standpoint, right? So the API that I showed you, it's really you're standing up the API and then you're using the API locally on ARMIS. So there's no firewall issue because you're on the same cluster. Now, if you try and connect to the API from your local machine, I don't think that'll work, if that helps. Okay, I don't think there are any more questions, so we will go ahead and end there. Again, thank you everyone for joining us, and we look forward to future talks with Midas. Thank you.